let's talk about the statistical interpretation of entropy. All right, let's look at it from a molecular perspective. What's exactly going on? Why does entropy tend towards a maximum according to the second law of thermodynamics? So far, we've only been looking at it from the point of view of heat, but exactly what's going on at the molecular level. So, um, entropy, statistically, you can define that as a measure of the number of ways that something can exist or happen. Okay. So, for example, let's consider a two-die toss. Okay. So let's say you have a pair of dice. Okay. And let's talk about the number of ways you can get a pair of snake eyes. How many ways can you get a two? One way. They both turn up one, right? So your outcome, let's say, if your outcome is 2, the number of ways that can happen is 1. How many ways can you get an outcome of 3? So you can have what? You can have 1 plus 2, right? Or you can have 2 plus 1. There's 2 ways, right? So 2 ways. How many ways can you get an outcome of 4? You can have 1 plus 3. You can get 3 plus 1 or 2 plus 2. So 3 ways. How many ways can you get an outcome of 5? 1 plus 4, 4 plus 1, 3 plus 2, 2 plus 3, 4 ways, right? How many ways can you get an outcome of 6? 5 ways. That'll be 1 plus 5, 5 plus 1, 2 plus 4, 4 plus 2, 3 plus 3. So 5 ways. How many ways can you get a 7? 6 ways. 1 plus 6, 6 plus 1, 2 plus 4. Oh, what did I have? 2 plus 5, and 5 plus 2, and 3 plus 4, and 4 plus 3. That is 6 ways, right? How many ways can you get an 8? 7 ways. Can you do 1 plus 7? There is no 7, right? And you can't get 7 plus 1 either. So what would be this? 6 plus 2, right? Or 2 plus 6. And then you can have 3 plus 5, and 5 plus 3, and 4 plus 4. You can only get 5 ways. How about a 9? There's only be 4 ways. A 10, 3 ways. An 11, how many ways can you get an 11? 2 ways. 5 plus 6 and 6 plus 5. How many ways can you get a 12? That's 1 way. Alright. So, if you are going to make a bet on a 2-die toss, what's your best bet? 7. That's why it's called lucky 7. Okay. Now, so the most probable outcome is a 7, right? So we say that that's the outcome that has the highest entropy. Okay. So how do we explain the natural tendency for maximization of S? It's really a question of probability. Okay, and you'll get into that deeper when you get to statistical thermodynamics. All right. So maximization of entropy really has something to do with probability. And when you're dealing with a lot of atoms, okay, you're looking at moles of atoms in your system, okay, then that fluctuations, you realize, okay, you're not always going to win if you bet 7, right? There's going to be fluctuations. But what happens is when you're dealing with a lot of atoms, this most probable outcome just becomes so predominating that essentially pretty much the only outcome for practical purposes you'll get. Okay? So, entropy, we said, is primarily a measure, is a number of ways that something can exist or happen. And in the case of atoms and molecules, how do we apply that concept? Well, it's primarily, in most cases, pretty much most cases, it's primarily a measure of the number of ways that you can distribute the thermal energy among the atoms in your system. So entropy is K, some constant K, times the natural log of the number of ways that you can distribute the thermal energy. What's the thermal energy? That's the difference between the actual energy of the system and its 0-point energy. So if you call your 0-point energy, for example, in a particle in a box, what was our 0-point energy? It's h squared over 8ml squared, right? So anything above that, the difference between whatever energy you have minus the 0-point energy, that's called your thermal energy. Okay? So if thermal energy is 0, then you say your entropy is 0. Why is that? If there's no thermal energy, how many ways can you distribute nothing to the atoms of your system? One way, right? Everybody gets nothing. That's one way, right? And what is ln of 1? 0. So you say the entropy when there is no thermal energy, all your molecules, all your atoms are in your lowest possible energy state at your 0-point energy. Then there's only one way of distributing the thermal energy, and natural log of 1 is 0. So that's what entropy we say would be 0. Okay. So what factors affect entropy? Like I said, primarily it's the total amount of thermal energy. Okay. The more thermal energy your system has, the more ways you can distribute the thermal energy, and the higher the entropy. Let's make an analogy. Let's say your money is energy, okay? Thermal energy. Let's say I have, let's say, 2 cents. Okay? And let's say there's only 2 atoms in my system. That's Joe and Catherine here. Right. How many ways can I distribute 2 cents between them? They each get a penny, or Joe gets 2, Catherine gets 9, or Catherine gets 2, Joe gets 9. 3 ways, right? 3 ways. All right. How about 5 pennies? More energy now. 3 and 2, 2 and 3, 4 and 1, 1 and 4, 5 and 0, 0 and 5. So there's more ways. So the more thermal energy you have, the more ways you can distribute it, the higher the entropy. And that is why, what did we say a delta S was if you add heat to your system? What's the formula we have? Integral of dq over T. Right? The higher the energy, the higher the thermal, by putting in heat into your system, okay, you're increasing the amount of thermal energy. So if your temperature goes up from T1 to T2, what happens to your entropy? Entropy increases, right? Now, what about number of atoms? If I have 2 pennies and I have 3 people to distribute it to instead of just 2 people, what happens? You have more ways of distributing it, right? So that is also another factor. Now, the 2 most common factors we really have to worry about, it would be this first and third one, because the second, in general, we're going to be looking at systems where the number of atoms is fixed, right? So we're only going to look at this first, pretty much look at just the first factor. And this second factor, this is important, quantization of energy. The closer the energy spacings, the higher the number of ways of distributing the energy. Okay? Let me give you an analogy again with money. Let's say Catherine and Joe don't want to take pennies. They're not going to accept pennies. Okay, so they'll only accept nickels. So 5 cents they'll take, but 1 cent, 2 cents, 3 cents they're not going to take. So they only take nickels. So the gaps between the allowed energies, the allowed amount of money I can give them would have to be at least multiples of nickels. Okay, they won't take 6 cents, they'll take 5 cents or 10 cents, right? So quantization, instead of pennies, you can only accept nickels, okay? Greater differences between allowed energy levels. Okay, so if I have 10 pennies versus, if I have, let's say, if let's say Catherine and Joe will accept pennies, and I have 10 cents to distribute, there's a lot of ways I can distribute those 10 cents, right? But if they'll only take nickels, how many ways can I distribute 10 cents between them? Joe gets 2 nickels, Catherine gets none. Catherine gets 2 nickels, Joe gets none, or they each get 1 nickel, and that's it. But if they were willing to take pennies, then I can give them 9 and 1, 1 and 9, 8 and 2, 2 and 8, 7 and 3, 3 and 7, 6 and 4, 4 and 6, 5 and 5, or 10 and 0, 0 and 10, right? So there's way more ways of distributing the energy. In other words, the closer the energy spacings, the higher the number of ways of distributing the energy, the higher the entropy. Okay? And to what do we associate closer energy spacings? Less quantization, smaller gaps between allowed energy levels. We associate those with less restricted motion. Remember from last semester, the more constrained a particle becomes, the bigger the gaps between the allowed energy levels. Okay? So the more restricted the motion, okay, the more you try to confine your particle, you get larger energy spacings. So what did we learn last time when we talked about quantum mechanics? We found that translational energy levels are pretty much essentially continuous, right? There's the gaps between allowed translational energies are very, very, very small for practical purposes. We can assume those are continuous. Rotational energies, the gaps between allowed rotational energies are slightly bigger, right? Of the order of a few reciprocal centimeters, right? So like this was 1 to 10 reciprocal centimeters. Whereas vibrational energy, those the energy differences would be what? H nu, right? For if you're assuming a harmonic oscillator, for example. And typically for molecules, what are the vibrational energy? What range of values do you get? From your IR spectrometer, what's the range that your IR spectrometer gives you? Mid IR is like 200 to 4,000 reciprocal centimeters, right? So you can see that's way larger than rotational energy level differences. And then electronic differences between allowed electronic energy levels would be even bigger. Okay? So the more restricted your motion is for your particle, the larger the energy spacings. In other words, the more restricted your particles are, then the fewer the number of ways you can distribute thermal energy. So that would mean what? This would mean lower entropy. Okay? So that is actually a better way of looking at the you've been introduced to the concept of entropy as being a measure of the order and disorder, right? So a better way to think about it is the more restricted the motions, the more restrictions there are in the motion of your particles, that means there's more order. That's a lower entropy. Okay? So more restricted motion, we say there's more order, there's less disorder, there's lower entropy. Okay? The more free your particles are to move, there's a higher entropy because the quantization there, the gaps between allowed energy levels are small. So let's predict delta S then based on that. If you do isobaric heating, no chemical or phase change. You're looking at the same number of atoms. What happens when you're doing an isobaric heating? Okay. Okay. Let's imagine an ideal gas. Okay. How do you make external pressure is constant. Your pressure is going to be constant. We're allowing your gas to expand, right? When you heat it. Okay. If you want the pressure to remain the same, you have to allow the gas to expand. So if you heat, temperature increases. So what's happening here? You have more thermal energy. Why? You have to increase the temperature, right? And your box is bigger now. Remember the particle in a box? The bigger the box, okay, delta E would be n plus 1 squared h squared over 8ml squared minus n squared h squared over 8ml squared. Okay, this length of the box right here, the bigger that length of the box, the smaller the gaps between the allowed energy levels. Okay, and you can see that visually. The bigger the box, the less restricted the motion of your particles. So your quantization then would be would involve closer energy spacing. So closer energy spacing means higher entropy. More thermal energy means higher entropy. So isobaric heating. Okay. What's the formula for entropy for isobaric heating? Delta S. Oops. Delta S is integral of dq over t at constant pressure, right? So you can see that that's going to be a positive number. Okay. What about isochoric heating? What does isochoric heating mean? Isochore means constant volume, right? So you go from here to here from same volume, right? And what's the only thing that's happening here? Temperature here would be higher than T1, right? Yeah, originally at temperature T1, you raise the temperature to T2. The volume remains the same, so your box remains the same. If your box remains the same, then the energy spacing remains the same. Okay? So temperature increases, so more thermal energy. Again, this more thermal energy here is what leads to higher entropy. Okay? This is one of those things that could be puzzling if you are thinking about entropy as just a measure of disorder. Because look, here you have a constant volume heating of an ideal gas. Okay, you know the motions of the molecules are random in the initial state, right? And so is it after you heat it. There's no difference. It's still just as random as before. So there's just as much disorder as before. So what happened here is the entropy change is not something that you associate with more disorder. It's just as disordered. The motions of the molecules are just as random before and after heating. Okay, but we say they have more thermal energy now. There's more ways of distributing the thermal energy. That's why you have a higher entropy. In the isobaric heating case, you have both factors in effect. Not only do you have more disorder, you've got a bigger room for the molecules to roam around, okay, and then so that leads to closer energy spacings, but you also have more thermal energy, okay? What about isothermal expansion? Well, what was the formula for isothermal expansion of an ideal gas? Nr ln V2 over V1, right? And that's a positive number. If V2 is larger than V1, then ln of a number greater than 1 would be positive. Okay, so we've shown earlier that this is going to be a positive. This is the formula for delta S for reversible isothermal expansion of an ideal gas, right? So reversible isothermal expansion, ideal, and has positive. So how do we explain it from a molecular perspective? Well, if your If it's isothermal, then your thermal energy is the same, right? So why is there an increase in entropy? Because you've got a bigger volume. A bigger volume would simply mean less restrictions on the motion of your atoms, the closer the allowed energy levels are. And the closer the allowed energy levels are, the more ways of distributing the energy, the higher the entropy. Okay? What about melting? Basically, what happens there is, okay, melting is an endothermic process, right? Energy that's drawn from the surroundings, what happens to it? It allows the molecules or the atoms to attain a higher potential energy. The thermal energy remains the same. What did we say about melting? Like ice melts, it stays at 0 degrees Celsius, right? Same amount of thermal energy. The energy that flows in is used to free the atoms from each other, so they end up with a higher potential energy. Okay? So, but now you have less restricted motion in the liquid. Okay? So less restricted motion, you have closer energy spacings, and that's why you have a higher entropy. When a solid melts into a liquid. Okay? So things that you associate with more disorder, those generally mean you're looking at the change in the quantization. More disorder means you're looking at closer energy spacings between the allowed energy levels. Okay. What about vaporization? Again, same thermal energy, right? So the energy that comes in, it's an endothermic process, is used to allow the molecules to attain the same thermal energy with more, but it becomes potential energy. They're allowed to separate more. Remember your intermolecular potential, okay? So if they're able to spread out more, your potential energy rises, okay? For the same amount of thermal energy. So same thermal energy, but you're going to have, again, closer energy spacings. If you change a solid or a liquid into a gas, what happens to the volume? Increases by a lot, right? So you're replacing highly restricted motion within the solid or liquid by more or less free translational motion in the gas. So translational energy levels, what did we say about those? Those are pretty much almost for practical purposes continuous. Okay? So that's how you explain the entropy increase during vaporization. What if you were to mix two ideal gases at constant temperature and pressure? The way you can do that is if you have same pressure here, P1, T1, and P2, T2. If they're the same, they're separated, and then you open this up, what happens? The gas will mix, right? So whatever gas you have on the left will just spread out throughout the box. Whatever gas you have on the right will spread out throughout the box. Okay? And if P1 and P2 are the same, and T1 and T2 are the same, okay, they're not just going to stay where they are, right? They're going to spread out and mix. So why is that mixing? Why is the entropy increase with that mixing? What happens when you remove the barrier between them? Each sample of gas will now have more room to move about. So there's less restrictions in the motion. If you can think of it as less restrictions in the motion of the molecules of the gas. So again, you're looking at a larger volume, okay? A larger volume for both gases. So they end up having closer energy spacings, and so delta S would be positive for that process. How about reactions? Well, we're going to focus on just the reactions at constant temperature and pressure. So you end up with products. We're going to compare products at the same temperature and pressure as the reactants. Okay? So, and since in a reaction no atoms are created or destroyed, you have same number of atoms and same temperature, reactants and products. So you're looking at the same thermal energy. Typically, if you have a reaction that ends up giving you more gas molecules, what does more gas molecules mean? Gas molecules are more free to move than liquids and solids, right? So if you have more gas molecules, you end up with closer energy spacing. So in other words, if you want to predict delta S for our reactions, you look at the effect of the reaction on the quantization of energy. Okay? you separate the effect of thermal energy. We're just going to look at it. What if the thermal energy doesn't change? What's the effect of the change in the quantization? So the more free, the less restricted the product molecules are, the higher the entropy for the reaction. Okay? And so generally, if you get more gas molecules or simpler molecules, okay, then you have closer energy spaces. They're more free to move. Simpler molecules you have less restrictions in the movement of atoms. The simpler the molecules are. The bigger the molecules, the more complicated, the more restrictions you have on the movement of the atoms. Okay. Isomerization, on the other hand, what happens in isomerization? Isomers are very similar. They're basically the same molecular formula. It's just a rearrangement of the atoms. So you would expect your delta S to be almost zero, very close to zero, except in cases where one isomer is more strained than the other. So for example, if I were to actually to predict the delta S for this, something like this, let's see, what's that molecule? And I want it to isomerize to that. What is this? The one on the left. How many carbons? 1, 2, 3, 4, 5. So that's a pentene. And where is the double bond? At carbon number 2. So this is 2 pentene. What is this one? This is 1 pentene. What do you think the delta S for this is going to be? It's going to be very close to 0. Okay? But if one isomer is more highly strained compared to the other, for example, something like maybe this, okay? What is this one on the left? This is 1, 2, 3 atoms, 3 carbons, C3H, instead of 6, since this is a double bond, this one unsaturation, C3H6, right? What is this called? Propylene. What is this thing? You got 1, 2, 3, that's also C3, and each carbon has how many hydrogens? 2, so that's C3H6. What would you call this one? Cyclopropane, right? What do you think the delta S for this? Yes. This is highly strained, right? You encounter this in organic. It's a highly strained molecule, so you would expect high degree of order there, right? There's a lot of restriction on the motion of the atoms there. So more restricted motion means lower entropy. So this will have a lower entropy. Cyclopropane would have a lower entropy than propane. Okay. So that's how you predict change in entropy. Two things you need to look at: amount of thermal energy and quantization, which you can gauge based on the extent to which the movement of the atoms are restricted. The more restricted the movement of the atoms are, the more complex the molecules. That means what? More order, lower entropy, bigger energy gaps between allowed energy levels. Okay, so you are replacing things like rotation and translational motion by vibrational modes, and you see that vibrational energy levels, okay, gaps between vibrational energy levels are way larger than gaps between allowed rotational levels or translational levels.